Hello class, today we're going to be looking at hexadecimal numbers. Now, we learned about binary numbers last time. We learned about, how to add them and just how to convert them into decimal and whatnot. Binary numbers can actually get very large very quickly. Even the number like 1000 and 1500 takes 10 bits to encode into a binary number. If I wanted to say read this number up here, it'd be quite hard. And so we have kind of a convention, and that convention is put spaces in between. But we could also put periods. That's another option for us as a way of making it easier to read. And what we do is every 4 bits we create a space, and we always start these 4 bits from the right hand side and then work our way to the left. So maybe the top bits may or may not be there or not. For example, if I had 1 1 0 1 1, I would break this up as follows. With the 4 bits down here on the right side, what I would not do is group the 4 bits on the left side first. That's not the way to group them. Okay, anyways, but it's still a lot of digits, even if we have this convention of periods or spaces. So, to deal with that, we're going to be actually introducing a hexadecimal number system. And hex you could think of as 6, decimal we know as 10. If we add them up, we get 16. And so that's what hexadecimal is. Hexadecimal is the base 16 number system. And just like we learned the other day, the way we deal with that is very similar to base 10, base 2. The place value of this digit would be 16 to the first. The place value of this, 16 squared. Place value of this, 16 to the third. And so we can just simply add up. We have 2 of these, we have 5 of these, and we have 9 of these. So by adding that all up, we get 8,281. But we have a kind of an issue or something we need to think about in terms of dealing with hexadecimal values. We have the numbers from 0 to 9, the symbols actually, from 0 to 9 to represent those quantity values. But how do we represent the quantity of 10 things? We don't want to write it as 1 0 because that's using these symbols here, and it's actually putting a 1 in this other place, and this actually would have a value of 16 in hexadecimal. So that's not something we would want to indicate the value of 10. So we could actually define maybe 10 to be some other symbol, maybe like a triangle. Then we can define 11 to be a square, and then we define 12 to be, I don't know, maybe a diamond. But that's not too great because, is a square bigger than a diamond, or is a diamond bigger than a square? It's kind of hard to remember that. So instead what we do is we use symbols that we're already familiar with. We use the letter symbols that we're familiar with already. And we know that C is bigger than B by 1, so that's a very convenient way of indicating or ordering those symbols. So that kind of leads us to this hexadecimal table here, where we have 0 all the way down to 9. Then when we run out of numerical symbols, we start using the alphabetical symbols from A to F to represent the values from 0 all the way to 15. Now it's important to be able to convert from binary to hex pretty quickly, and so what you really want to do is you do want to memorize, or not memorize, learn how to create this table. Learn how to write out the binary values from 0 0 0 0 all the way to 1 1 1 1. So when you have 0 0 1 1 0 0 1, for example, what's the next value? 1 0. Well, I can't put a 2 here, so I need to move the 1 over, and then I have my next value, and then I have like that, 1, 1, 0, 0. So just kind of learn quickly how to write the incremented value from, in this case, 9 to 10 to 11 to 12. It takes a bit of practice, but you'll get used to the pattern if you do it a few times on a piece of paper. Okay, so then how do we convert a binary number to hex? Suppose this is my binary number. Basically what I do is I just start from the very left-hand side here, and I work my way across, grouping them in groups of 4, always starting from the right. And I may, in this case, I have a even number divisible by 4, groupings of 4 bits, but it might be that this last bit does not exist. In that case, you just think of it as a 0. Okay? So you just look it up in the table. This converts to the value e. This is 1. This is 10, which is a, and this is 9. Now we do have a convention to indicate that we're looking at a base 16 number. We can put the 0x in front of it to indicate that. Now why do we need that? Now in the case where you see a number with letters in it, you can kind of automatically assume that it's base 16. But suppose you have a number like this. You know, is that base 10? Is it base 8? What base is it? So you could do the following. You could put a little subscript here like we learned in the last lesson. Or this new concept is we put a 0x in front of it as a way of indicating that it's hexadecimal. And this is very convenient because some text editors, it's a little hard to create this subscript 16. So instead of doing that, we just type in a 0x. How do we go from hexadecimal to binary? Same thing, but just in reverse. We look it up in a table. So we see that E is this, this is 2, this is 4, and this is A. So again, having a table in front of us really helps us do the conversion fast. If you practice this for a little bit, you can actually start memorizing the values and they'll come naturally to you. Okay, so where is hexadecimal used? Actually, in computer science, hexadecimal values are used all the time. I would say that it's actually used more so than just binary numbers because, like I said at the very beginning, binary numbers get so long. I mean, just think about a 32-bit binary number. It's too long. A specific example might be colors. Colors are something that we encode using 24 bits. We have 8 bits for red, 8 bits for green, 8 bits for blue, and if I wrote them out as 24 bits of ones and zeros, it would just be really unreadable. So instead, it's pretty nice. Red is 2 hex digits, green is 2 hex digits, and blue is 2 hex digits. So we have some examples here. Actually, here's yet another way of indicating hexadecimal. This is kind of similar to writing 0x, but it's just yet another kind of writing convention. So we have our red component here, red, green, and blue. And you notice that it's in hex, so we see here the value FF means 255 in this case. We have 8 bits. 2 to the 8th, that's equal to 255. So I could, 256, and I could represent 256 different numbers with 8 bits. And if I start with 0, I can get all the way up to the maximum value of 255. Hence, FF is the highest value, 255. Okay, so that's the lesson for today. Have a good day, class.